All right, so this is the second video on indeterminate forms and L'Hopital's rule. So let's say we wanted to evaluate a product of two functions where one goes to 0 and one goes to infinity. Well, that's really tricky because you don't know which one goes to which faster, okay? So if it goes to 0 faster, then the whole thing goes to 0, infinity. So there's just this indeterminate form. We can't determine the exact behavior of that product, okay? So for example, if we have like some polynomial and then you're multiplying it by this function here, when you simplify that, you'll end up having 3x squared in the top and x to the n plus 1 in the bottom. And you can see here, there's a couple different scenarios. If n equals 2, well, then we have the same rate. So we would have 3 over 1 if you kind of use that horizontal asymptote rule. If n is 1, well, then the whole thing goes to infinity. And if n is 3, then the whole thing goes to 0. So you can see like there's a whole bunch of different scenarios that might happen depending on what this value of n is. So we need to have a way to look at this further. We're going to use L'Hopital's rule in order to do that. But in order to use L'Hopital's rule, we need a function on the top and a function on the bottom. So you'll see in this first example I have for us, there's a multiplication, but if when you very first look at it, you might not see a function on the top and the function on the bottom. It looks just like a product. If I plug this in as I go to 0, I end up getting 0 times, and then our cotangent graph goes to infinity as we approach 0. Okay, so instead, I am going to write this as cotangent is 1 over tangent. So x times 1 over tangent x means I can look at this as the limit as x goes to 0 of x over tangent x. Now, again, when I plug in, I get 0 over tangent goes to 0 there with our vertical asymptotes. I should have those dashed. So I can use L'Hopital's rule now because I have a 0 over 0 indeterminate form, derivative of the top, derivative of the bottom, secant squared. All right, secant squared as a graph is 1 over cosine. Oh, we could just flip this and let's just do that instead of looking at a graph of cosecant. Let's just make this the limit as x goes to 0 of cosine squared. That makes more sense. Cosine of 0 is 1. Square that, we get 1. Okay. All right, also, if we have any kind of weird like infinity minus infinity, same kind of situation, and you can read through this and pause if you would like to, but it's the same kind of battle of, well, if it's bigger than 2, this happens. If it's equal to 2, this happens. If it's less than 2, this happens. And so we have to have a further analysis or evaluation of what's kind of going on here. So let's look at an example. If I plug in, remember the first thing we're going to do is we're going to go ahead and plug in. So if I plug in 0, I get infinity minus 1 over something that goes to 0, infinity. That is an indeterminate form. Okay, so I need to make this into an f of x over g of x situation in order to use L'Hopital's rule. I'm going to do that by finding a common denominator. So I'm going to multiply this first by tangent x over tangent x. I'm going to multiply this second by x squared over x squared. And let's see, I have the limit as x goes to 0 from the right of tangent x minus x squared all over x squared times tangent x. Now, if I plug in 0, I get 0 minus 0 all over 0. I can apply L'Hopital's rule here. So I'm going to have the limit as x goes to 0 from the right, derivative of tangent is secant squared, minus derivative of x squared is 2x, all over, I'm going to have a product rule, derivative of the first times the second, plus the first times the derivative of the second. Okay, so now when I plug in 0 from the left in the top, secant squared ends up going to 1. You can look at a graph for that, minus 0. All over 0 plus 0. And anytime we end up having a number, so this is going to be 1 over 0, this whole thing is going to end up going to infinity. All right, one more type of indeterminate forms. Anytime you have like a function to another function where you're going to have 0 to a 0, infinity to a 0, 1 to an infinity, all of those are going to be indeterminate forms. Okay, so one thing that we're going to do is we're going to get really fancy here with logs. Remember, there's the log rule that log of x to a power is the same thing as p times the natural log of that function. And so you can see what we're going to end up doing here. If you take the natural log of both sides, we can then bring this power in the front. And then we're going to probably have a situation where we have a 0 times infinity or something of that form that we were just talking about. Okay. Then you can just take the derivative, or excuse me, the limit here. And then if you need to use L'Hopital's rule, you can do so. Okay. There's more things here from the text. I really just want us to go ahead and get into an example here. So if I were to plug in infinity, okay, I would end up getting infinity to the 1 over infinity or infinity to the power of 0. And that's just really tricky. Like that's not, that we call that an indeterminate form. I need further analysis to know what's kind of going on here. So I say, let's let y be equal to x to the 1 over x. And if I take the natural log of y and the natural log of x, 1 over x, then I get that this is 1 over x times the natural log of x. So now let's take the limit of both sides. The limit as x goes to infinity of the natural log of y, we say is equal to the limit as x goes to infinity of, I'm going to write this as the natural log of x over x. Now be careful, don't be like, oh, and the x's cancel. Nope, natural log is a composite function. Natural log of the argument x over x. It is not a multiplication in the top, but it is infinity over infinity, so I can use L'Hopital's rule. The derivative of the top over the bottom. So I get the limit as x goes to infinity of the natural log of y is equal to the limit as x goes to infinity of 1 over x, which is 0. All right, let's go ahead and go back up and see what we need to do for our next step, because that's the natural log of y, right? Like that's not exactly what I want here. I need to be able to undo that. Okay, so here's the trick. So this is where we are in our problem, right? We have the limit as x goes to infinity of the natural log of y equals 0. Well, with log rules, since log is a continuous function, it's okay to kind of interchange these, okay? And there's a proof if you want to know why, but it is okay to interchange these and say, well, that's the same thing as taking the natural log of this limit. Well, I undo natural log by taking e on both sides. And so I get the limit as x goes to infinity of y is e to the 0, which is 1. And so that's where this piece of that step is going to come into play. Tricky for sure, but another indeterminate form, and this is how you would solve it using that log trick here.